Have you ever looked up at the night sky, at the countless stars scattered across the immense darkness, and felt a profound sense of wonder? It is a feeling that has connected humanity for millennia. We are a species driven by curiosity, a desire to understand our place in this vast cosmos. We have built great telescopes to peer into the distant past, and launched probes to visit our planetary neighbors. But what if we could do more? What if we could go beyond just observing the universe? What if we could actually shape it, mold it, and bend its fundamental rules to our will? This is perhaps the ultimate human dream, to transition from being passengers on a tiny blue dot to becoming true masters of our cosmic destiny, capable of engineering the very fabric of reality. This question may sound like it belongs in the realm of science fiction, something you'd see in a blockbuster film or read in a fantastical novel. And for most of human history, that is precisely where it has stayed. The laws of physics, as we understood them, seemed rigid and unbreakable. But in the last century, our understanding of the universe has undergone a revolution, revealing a reality far stranger and more flexible than we ever imagined. Albert Einstein, with his theory of general relativity, completely shattered this old view. He showed us that space and time are not independent. They are intricately woven together into a single four-dimensional fabric he called spacetime. Think of spacetime as a gigantic, invisible trampoline. This trampoline is the universe itself. It's not empty, and it's certainly not rigid. It has texture, and it can be stretched, bent, and warped. Every object with mass creates a dent or a curve in this sheet. The more massive the object, the deeper the dent it creates. What we perceive as the force of gravity is simply objects following the straightest possible path through this curved spacetime. This is exactly what happens with planets orbiting the Sun. The Sun is so massive that it creates a huge depression in spacetime, and Earth, along with the other planets, is simply following that curve. Even light, which has no mass, must follow these curves, which is why its path can be bent by the gravity of massive objects like stars and galaxies. Einstein's revelation that space could be bent and stretched by gravity had another, even more mind-bending consequence. Because space and time are inextricably linked in the fabric of space-time, anything that affects space must also affect time. The clocks on GPS satellites, which orbit high above the Earth in a weaker gravitational field, actually run slightly faster than clocks on the ground. If engineers did not correct for this relativistic effect, GPS navigation would fail within minutes. If you were to board a spaceship and travel at nearly the speed of light, your clock would tick much more slowly than the clocks of your friends and family back on Earth. When you returned, you would find that you had aged only a few years while decades had passed for them. If we want to build something as incredible as a warp drive or a wormhole, ordinary matter simply will not do. To create the kind of space-time geometry needed for faster-than-light travel or cosmic shortcuts, we need to do the opposite. We do not want to create a dent. We want to create a hill. This requires something that sounds like it has been lifted straight from a comic book: exotic matter. This is not just matter that is rare or strange. It is a hypothetical form of matter that violates the rules we take for granted. Its defining feature is that it would have negative mass, or equivalently, be associated with a region of negative energy density. If you could hold a lump of it in your hand, it might push away from the Earth instead of falling towards it. For a long time, the idea of negative energy was purely theoretical, just a strange quirk in the mathematics of quantum theory. That all changed with the experimental confirmation of a phenomenon known as the Casimir Effect. Two perfectly flat, reflective metal plates are placed parallel to each other in a vacuum, separated by a microscopic distance. The quantum vacuum is filled with virtual particles of all possible wavelengths. However, the tiny gap between the plates acts as a filter. This creates a tiny patch of negative energy density relative to the surrounding vacuum. The higher energy pressure of the vacuum outside the plates pushes them together. This force has been precisely measured in laboratories, confirming Casimir's prediction. The idea of a warp drive was given a solid mathematical foundation in 1994 by the Mexican theoretical physicist Miguel Alcubierre. He was a huge fan of the television series Star Trek and was inspired to see if the show's iconic warp drive could actually be made consistent with the laws of general relativity. Alcubierre's model works by creating a region of expanding space-time behind the ship and a region of contracting space-time in front of it. The spaceship itself would rest peacefully in a pocket of flat, undistorted space-time inside the bubble, protected from the mind-boggling tidal forces just outside. Think of it kind of like a surfer on a wave. The Alcubierre drive would create its own wave in the fabric of space-time. While a warp drive offers a way to travel across the vast cosmic ocean, another, perhaps even more radical idea offers a way to bypass the ocean altogether. This is the concept of a wormhole, a hypothetical tunnel or shortcut through the fabric of space-time. Imagine space-time is a large sheet of paper. If you could fold the paper over, bringing two distant points very close together, and then punched a pencil through the paper, you would create a short tunnel connecting the two distant locations. However, these theoretical wormholes were found to be incredibly unstable. They would pinch off and collapse into a black hole so quickly that not even a single photon of light would have time to pass through. Even if we solve the fundamental physics and discover a reliable way to create negative energy, we immediately face a challenge of truly astronomical proportions: the energy cost. The early models for the Alcubierre warp drive required a quantity of negative energy equivalent to the total mass energy of a giant planet like Jupiter. This is a scale of energy manipulation that is so far beyond our current capabilities that it is difficult to even comprehend. It places the technology firmly in the realm of a Type 3 civilization on the Kardashev scale, a society that can command the energy output of its entire galaxy. Our most powerful particle accelerators, which consume the energy of a small city, are like children's toys compared to the cosmic engineering tools required. Let us assume for a moment that we solve the energy problem. The next monumental challenge is one of stability and control. The theories for warp drives and wormholes require this material to be sculpted into incredibly precise and dynamic shapes. Any small imperfection or fluctuation in the negative energy field could lead to a catastrophic collapse. The wormhole could snap shut in an instant, or it could develop instabilities that would unleash torrents of lethal radiation, incinerating any ship or traveler inside. Furthermore, there's the problem of quantum instability. The presence of a warp bubble or a wormhole throat would create a feedback loop of virtual particles, causing the energy in that region to spike uncontrollably towards infinity. Finally, even if all the technical and scientific hurdles could be overcome, we would face a set of profound ethical and societal challenges. The power to engineer space-time is the power to reshape reality, and such a technology would irrevocably alter the course of human history. Who would control this technology? Would it be a tool for all of humanity, used to explore the cosmos and unite our species? Or would it become the ultimate weapon, controlled by a single nation or corporation, creating a permanent and insurmountable gap between the haves and the have-nots? The potential for time travel, however remote, raises even deeper questions. A wormhole could theoretically be manipulated to become a gateway into the past. This opens the door to the grandfather paradox and countless other causality-violating scenarios. The journey to the stars may require not only a revolution in our physics and engineering, but also a revolution in our wisdom and our understanding of our place in the cosmic order. We would need a level of collective wisdom and self-control that our species has yet to demonstrate. Before we can responsibly wield the power to bend reality, we must first learn to manage ourselves and our own planet. The challenges are not just out there in the cosmos, they are right here, within us. Perhaps the greatest challenge of all is not in mastering space-time, but in mastering ourselves. We began this journey with a simple yet profound question. Can we, a species born on a small rocky planet, ever learn to engineer the very fabric of the universe? We have traveled from the familiar world of gravity and planets to the strange quantum realm of negative energy and space-time foam. We have seen how the dreams of science fiction, like warp drives and wormholes, are not pure fantasy, but are rooted in the elegant, though incomplete mathematics of our best physical theories. The journey has shown us that reality is far more pliable, more mysterious, and more magnificent than our ancestors could have ever imagined. It is a universe that seems to whisper of untold possibilities. The path from our current understanding to becoming true architects of the cosmos is fraught with challenges that are almost beyond comprehension. We stand before these hurdles like an ancient human standing at the edge of the ocean, dreaming of visiting the lands beyond the horizon. Yet the dream persisted, not because it was easy, but because the call to explore is written into our very DNA. The pursuit of this knowledge, whether or not it ever leads to a functioning warp drive, will inevitably lead to discoveries and technologies we cannot yet foresee. We are no longer just dreaming. We are calculating, experimenting, and pushing the boundaries of what is known. The science of spacetime engineering is in its infancy, a field of tantalizing clues and immense obstacles. So we are left looking up at the sky, just as our ancestors did, filled with a sense of wonder. But our wonder is now deeper, enriched by a century of scientific discovery. We see not just points of light, but distant suns and galaxies. We see not just empty space, but a dynamic, flexible fabric of space-time. We do not know what the future holds. We do not know if we will ever become the masters of the cosmos. But we do know that the desire to ask the question, to dream the dream, and to take the first tentative steps on the journey is what makes us human. And that journey of discovery will and must continue.